Welcome to this video. We're going to solve some problems on the Doppler effect. The graph below shows wavelengths of light received at Earth. The light was emitted by a galaxy receding away from Earth. So here's the first wavelength that is received. Who knows, maybe it's 100 nanometers. Here's the second wavelength, maybe that's 400, just making this up. And there's the third, which is maybe 900. This is a wavelength graph, a wavelength axis. The farther to the right, the higher that value of wavelength. Draw lines A star, B star, and C star, showing the wavelengths that were emitted. First, what were shown on this graph are wavelengths. The lines A, B, and C represent the received wavelengths. When you look at the sky, these are the colors that you see. These are the received wavelengths. Now I've written above lambda prime. In general, there are two variables we use for wavelength. There's lambda prime and regular old lambda. Lambda prime represents the received, or we might also say the observed wavelength, and that's the one that's been shifted from the original. Plain old lambda, on the other hand, represents the emitted wavelength, how it starts out. You could think of it as the original value, or the unshifted wavelength. So what we're looking at in the graph, the three lines A, B, and C, those are the wavelengths that you see in your telescope. Those are the observed shifted values. If they're shifted, then they didn't start out at those values. They weren't originally 100, 400, 900. Either they started out at a lower wavelength and they were shifted up, or they started at a higher and they were shifted down. The way we figure out which occurred is by looking at the next question. Is there recession or is there approach? The problem says the galaxy, the source, the thing that sends out light, recedes. Recession is what we have here. By the way, galaxies you can think of as just giant collections of stars. So they send out a lot of light. Not just one star, but many, many stars. Okay, so the galaxy, which sends out light, is receding. The next thing you do is, and then what are we drawing in? The lines A star, B star, and C star. Those are supposed to show the emitted wavelengths. So plain old lambda. Where do we draw the new lines? If there is recession, then it looks like this. The galaxy is moving this way, and the wavefronts are compressed in the direction that the galaxy goes in. If the galaxy moves to the right, then the wavefronts are compressed on the right side, and they're expanded on the left side. If the galaxy were going the opposite way, the picture would be reverse, like this. Whichever way the galaxy goes in, that's the direction where the wavefronts are compressed. By the way, wavefronts, the term wavefronts, refers to the circles. These circles themselves are the wavefronts. They're like the front of one wave. Okay. If there is recession, that means the galaxy moves away from Earth. So here's Earth, and the galaxy's going away. The Earth, from the perspective of the Earth, these wavefronts arrive, and they are really expanded out. The wavelength, the distance between two wavefronts, the wavelength is much, much larger. So we see a larger wavelength. The observed wavelength is bigger than what's originally emitted. So here in purple, line A, there it is, that's bigger than the original lambda. The original lambda, A star, should be right here. And it's been shifted up to a larger value because of that expansion of the wavefronts. And likewise, this line B, we are seeing a longer wavelength than was emitted. the emitted wavelength was here, and because of the recession, it was shifted up to a higher value. C, the same situation. It started out as a lower wavelength, and it was shifted up. So here's the idea. If you look at a galaxy, you're not going to see just one single color. You're not going to see one single wavelength. You're going to see many different colors, right? And each of those colors will have been shifted. And the interesting thing is that the higher the wavelength, the larger the shift. So if you look at, 900 nanometer, if you look at, let's say, something with a really high wavelength like red, the red will be shifted more than blue because red has a higher wavelength. So, so the red will be shifted more. Now, how do we know that that's true? We have an equation that says the amount of wavelength the amount of shift in the wavelength, the change, is equal to the emitted value, right? Like red or blue wavelengths, times the speed of the source, the speed of the galaxy, over how fast the waves go in the medium. For EMR, electromagnetic radiation, this is obviously 3 times 10 to the 8. That's how fast the light waves go through the vacuum of space. Okay. So as we move to the right, as we go to higher and higher lambda values, there's a bigger shift. As this increases, the shift increases. High lambda, high shift value. Small lambda, small shift. So let me finish labeling my diagram, and now we'll move on. The graph below shows wavelengths, dealing with wavelengths, that are received at Earth. So I have 3 lines. We are looking and seeing 3 different colors. 3 wavelengths are received. Because they're received, I mark them lambda prime. The light was emitted by a galaxy approaching, this is a typo, approaching the Earth. Draw lines showing the wavelengths that were emitted. We have to draw lines showing the values, the original unshifted value of lambda. Approach looks like this. Here's the galaxy moving toward the Earth. The wavefronts are compressed in the direction the galaxy goes in. And so, when those wavefronts reach the Earth, they are all really, really, really compressed together. Wow, it takes a long time, for the light to get there. And so what the Earth experiences is wavefronts that are really close. In other words, the received or observed wavelengths, distance between 2 fronts, is smaller than what's originally sent out. There is compression because of the approach. And so the values I've shown, A, B, and C, these lines, these values on the axis there, okay, those values are smaller. They started out bigger. Here's the original unshifted value, and then it got smaller. It was shifted down because of the approach. Likewise here, we started big, shifted down, and here started big, shifted down. What we had to draw were the original values, which were bigger. Because they were bigger, that means they were farther to the right on the axis. Okay. Next one, the graph shows wavelengths, still dealing with wavelengths, that have been emitted by a galaxy. So now we are looking at the emitted values, the unshifted original values. Those emitted wavelengths are received at Earth. Okay. And the galaxy is receding away from Earth. We have to draw the received wavelengths, draw the shifted values. If the galaxy recedes, it moves away from Earth like this. The wavefronts are compressed in the direction that the galaxy moves in, right? And so the waves that hit Earth, and then they keep going, from the Earth's perspective, these waves are really far apart. The wavefronts are expanded, And so what we see are bigger wavelengths than are originally emitted. Because of the recession, because the galaxy recedes, the values that we see, which we have to draw in, right, we're drawing lambda prime, they are bigger, so farther to the right on the graph. Here's a prime, and we know from before that the farther to the right we go on the graph, the bigger the shift. My lines are not very straight, are they? So when a very large value is sent out, it is shifted a large amount. When a small wavelength is sent out by that receding galaxy, the shift that we see, that we observe, is small. The graph below shows wavelengths, still wavelengths, that have been emitted by a galaxy. These are the lambda, plain old original lambda values, unshifted, emitted. The galaxy approaches Earth. So let's draw the picture. Here's the galaxy. Wait, it's going the other way. It's approaching. Approaching the Earth. Here's the Earth. The wavefronts are compressed in the direction that the galaxy is moving in. So they're compressed on this side, right? And they're expanded over here. Now, the wavefronts should all be equally spaced on the left. The compression amount doesn't really change as long as the galaxy has a fixed speed. Okay, so what do we see at Earth? We see compressed wavefronts and a smaller wavelength. So the wavelength we observe is smaller, and we have to draw that smaller lambda. If it starts out at 100, it gets smaller, it shifts down. So there's the shifted, observed, or received wavelength. This one gets shifted down, but it's shifted more. And that's B star. This one is shifted even more, because as we know, right, the amount of wavelength shift, whether positive or negative, just the raw amount, we could even put absolute values if we wanted, the amount of shift is directly proportional to the wavelength that is sent out originally. So if you send out a big wavelength, you get a big shift. Okay, now on to something different. This graph shows frequencies of light that are received at Earth. Where did the light come from? It was emitted by a galaxy receding away. So we're looking at lines A, B, and C, which represent the frequencies that we receive at Earth. Those are the received, or F prime, values. We have to draw lines showing the frequencies that were emitted by the galaxy. The galaxy is receding away, so we'll draw that like this. The Earth is on the left, galaxy is on the right, galaxy is the one moving. Because the galaxy moves to the right, the wavefronts are compressed on the right side of the galaxy, and they're expanded on the left side of the galaxy. Now, as we sit here on Earth, those wavefronts, they move out and they strike us. But because those wavefronts are expanded due to the recession, we are struck with wavefronts less frequently. They arrive less frequently. So the observed or received frequency is lower because the wavefronts hit us less frequently due to the wavefront expansion. So here we've shown F prime values, A, B, and C. These lines are the F prime values. We have to draw in F values, right? Emitted frequencies. We have to draw them in which are bigger. So here's how I'll draw that. It starts out bigger and then is shifted down. This starts out bigger, and because of the recession, the frequency is shifted down. This starts out bigger. Because of the recession, it's shifted down. And just like before, the amount of frequency shift is proportional to the value of frequency that you observe. If you observe a big value of frequency, there's a big shift. If you observe a small value of frequency, then that means there must have just been a small shift.